So today we are going to talk about type systems. And I'm really excited about this because I've had a couple attempts at getting this topic ready. It's such a deep topic and you can go all kinds of different directions with it, but I think we'll kind of see where we go today. But this is one that I put a lot of time into kind of researching and figuring out the best way to talk about it. But type systems are pretty cool. Whenever I first started programming, I learned C++. And so types to me at that time were, you're working with integers, you're working with strings, very primitive types. You're working with pointers and memory structures. And then later got into like C#, .NET, Java. You're working with objects and class types. And really that was kind of the world of the type system at that point. You have design patterns which kind of leverage some of the benefits of the type system. Whenever I got into functional programming, though, was when it really opened up my mind to how sophisticated type systems can be. So I started programming in Scala several years ago, and I was like, wow, there is a lot to learn about types that I didn't know before. So languages have come a long way since. And so today I would like to do kind of a high-level survey of what is a type system. And we're going to look at different type systems that are out there and then slide into how does functional programming impact the design of a type system. So I'm going to start out by reading 3 quotes. I'm going to do something that you're not supposed to do in a live presentation and read from the slide, okay? I'm going to read 3 quotes about type systems, but they give us different facets about what a type system is, and I think they're important to understand the different facets. So first quote, a set of rules that assigns a property called a type to the various constructs of a computer program, such as variables, expressions, functions, or modules. These types formalize and enforce the otherwise implicit categories the programmer uses for algebraic data types, data structures, or other components. Ooh, okay. So I heard variables, functions, or modules, all right? So I think if most of us in here are comfortable with programming languages and general programming languages, we can kind of understand what's going on here, right? Okay, now this next one. A type system is a tractable syntactic method for proving the absence of certain behaviors by classifying phrases according to the kinds of values they compute. Ooh. Okay, that one's a little deeper, all right? This one comes from a foundational book based on type theory called Types in Programming Languages. In fact, if you're interested in getting into type theory, that book is available online. It's considered kind of one of the de facto defining books about it. And this is where mathematics and logic systems begin to blend with computer systems. So it sounds very much like we're describing a proof here. So if you're common with a mathematical proof, the idea that a type system can correlate with mathematical proofs, and so you can write programs that are therefore provable. All right, so that's the angle that this is taking. And then lastly, this isn't necessarily a definition of a type system, but it describes what is important for a type system. Intuitively speaking, you want your type system to induce a system of logic that is consistent. That is, doesn't allow false theorems to be proven. The more inconsistent the system of logic induced by the type system is, the less useful the type system is as a proof of correctness of the code. In other words, the more strict, sophisticated type system you have, the more consistent output you're going to get. And then the opposite is true as well. So I think this quote is one of the reasons we should study type systems and understand and utilize the type systems whenever we build things. In my first talk a long time ago, I talked about how we as software developers are builders, right? We're not syntactic experts, we are builders. We're building things. And so the more we understand about how to build things and build things better, the better we will be at our profession and what we do. So what are the goals of a type system? Some of these are pretty obvious, right? We want to check for bad behavior. We want to do that as early as possible so that we learn about the problems in our program at the time of writing the program and not having our users do it. We want to enable abstractions. So I don't want to have to talk to the computer in ones and zeros. I would like to use integers and strings. I'd like to use objects. I would like to use expressions. All right, so the type system enables me to do that. And also, it provides documentation. The more sophisticated type system you have, the more documented your code is going to be, because the code is going to represent the truth, right? When you add code comments, and that's your primary mode of documentation, it's easy for that to drift over time or be inconsistent. Maybe the code comments captured the developer's perspective of what's going on, but it may not really be what's happening. So a good type system also helps you self-document your code better. Okay, question to all. What are some of the things that we do to evaluate if we're going to use a programming language? I'm going to open this up to the floor. What are some ideas? When you're evaluating to use a particular programming language, what are some of the things that you look for? Community. Very good. What else? Flexibility. Okay, so it solves the type of problem we're trying to solve. Speed. Okay, so how approachable is it? Okay, so the availability of expert developers, people that know the language and are going to proselytize it. Mm-hmm. Yeah, this is the list I came up with. The very first thing you're probably going to do is you're going to evaluate the domain of the language. All right? Is this a language that solves the problems I'm trying to solve? If I'm going to write a web page or client-facing logic, I'm probably not going to choose C++. All right? People do that, but you're probably not going to choose that as your first choice. You're probably going to choose from a language in the JavaScript family, because that is the domain that language was created for. If I'm going to do intensive data processing and I'm going to use a lot of asynchronous operations, I'm probably not going to choose JavaScript. Okay? Because that's not the domain that language was written for. So the first thing you're probably going to look at is the domain that the language fits in. The second thing is community. So whenever I got the domain and I got a family of languages, we all know there's those languages that are experimental, they're really cool looking, but there's 5 guys in a garage that use that language and maintain it, right? So you're going to probably choose a language that has a large community, a lot of experts. They're going to blog about it. They're going to put a lot of documentation out there. Okay? And I'm going to argue this third point is type system. Okay? We might favor certain syntax, but really it's the type system next that we're going to care about. What does the language offer us as building tools? If you get anything from this talk today, this is the one thing I want you to get. The more you use your type system, the more it works for you. All right? If you use your type system primitively, don't expect anything beyond primitive behavior from your type system. So if you use rich types and rich type system features to describe your domain, then you'll find your type system actually enforcing your domain. And I think that's very important. Okay, so I'm going to set a few expectations here of what we're going to do. We're only going to scratch the surface, and I'm not going to get super deep in the type theory. We're going to bounce on it, but we're not going to go super deep here, okay? There is a lot when you start studying types that you can go into. There are books and books. There are PhDs that get into this. So we're just going to scratch the surface, and we're going to make it relevant to software development. I am a Scala developer. I am comfortable in Scala, so any code you see is going to be in Scala. However, I am not going to use anything that is outside of the standard library, and I'm not going to use anything that is easy to understand, and also I'm not going to do anything that's specific to Scala. So what I'm saying in Scala today is also applicable in Haskell, F#, and a lot of the other languages we use. Okay, so I'm going to keep this as language agnostic as possible, but I got to be able to speak in something. All right, so we're going to start today with fundamentals. All right, so just the basics. Most basic type systems support these 3 things: type safety, static versus dynamic type checking, and type inference. When we're talking about type safety, a safe language is one that protects itself from its own abstractions, all right? So let's think about safe versus unsafe behaviors. C++, I'm going to pick on it for a minute. Very unsafe language, all right? In C++, I can dereference null pointers. I can access arrays out of bounds. I can return memory locations out of a function that don't belong to the scope of the function. I can use uninitialized variables. I can also, at will, cast between and reinterpret memory addresses into different data types, right? That is very dangerous behavior. In fact, it's not going to be something caught at compile time, and at runtime, you're not going to get an exception. It's going to crash your program, or worse yet, open you up to exploits, all right? The last one is me poking at JavaScript. It doesn't check parameter lists, so when you get to a function, you have no idea what was passed into that function or how many parameters, right? So these are unsafe behaviors. And on the other side, safe behaviors are languages that are going to catch exceptions. We're going to disallow uninitialized variables. At compile time, we're going to check parameter lists. We're going to check types. Okay, those are safe operations. Now, when we are evaluating a language, it's not a binary characteristic, right? It's not that this language is unsafe and that this language is safe. There are aspects of the language that favor safety, all right? So it's kind of a lot of shades of gray, you know, memory safety, abstraction safety, runtime safety. All right, this one. Static versus dynamic type checking. Static type checking, we verify the program is safe before execution. Dynamic, we're going to do it at execution time. All right, so question to the audience. Why do we get in so many religious arguments about static versus dynamic checking? I'm trying to be a troll, don't swing for it. All right, more seriously, pros and cons of static versus dynamic type checking. This is a serious question. Exactly, exactly. So, yeah, so so pretty much this. Aaron summed that up very well. So essentially with static type checking, you're going to get very early feedback if there's problems in your code. You're going to get more optimizable code because less guesswork has to be done at runtime. But you're going to have to annotate your code a lot more, and that test compile cycle is going to be a little bit longer. Now, dynamic type checking, on the other hand, it's very quick, on your feet, off the cuff. You can do a lot of different type introspection. You get duck typing. If it looks like this, you can change things at runtime. It's fantastic for prototyping. But you're also going to have to write a lot more unit tests to do things that a statically typed type system would check for normally, right? You don't want to be at runtime and not have any unit tests, and it turns out you're getting crazy types passed around everywhere. They're really for different kinds of applications. You got to think about that. Here are just some languages that are static versus dynamic. I think most of us are probably familiar with a lot of these, so I'm not going to spend too much time here. Okay, this last one I threw in just because I don't feel like it'd be complete if I didn't mention it. Strong versus weak typing. The community generally says this is a very bad description because it's very unclear what it means. But essentially, my ability to reinterpret a type of a variable at runtime, all right? So in a static, strongly typed language, I'm not gonna, once I assign a variable a value, I can't change the type of that value. Whereas like if I'm in C++, I can change it. I can reinterpret cast that memory address into something else, or I can use unions or other things that let me do that. JavaScript, whatever. Whatever, whenever, all right? Yeah, so you get the idea. Okay, so again, shades of gray. It's kind of all over the place, and languages cover these in different areas a little bit differently. Okay, and then last one of the basics I want to talk about is type inference. This is a benefit of statically typed systems where I don't have to annotate all my types explicitly, but they can be inferred based on what's on the right. Okay, so down on the left, you can see I put types at the end of my variables, and on the right, I didn't put any types, but the compiler is able to figure out what that is. Okay, that is still a feature of static typing language. A lot of people confuse that with dynamic typing. It's different. This is static typing still. It's done prior to execution, but it's just the compiler is being super smart and figuring out what I got. The biggest benefit of this is, and we as functional programmers know this, is that whenever you're doing functional programming, you don't have to tell the computer how to do every little step of something. So for instance, when I'm in an imperative programming language and I'm doing a loop, I have to describe exactly how that loop is going to work. All right? I have to have a counter, I have to have an increment, and I've got to kind of follow through there. In functional programming, we like expressions. So what is it that I want done? And I'm going to let the compiler figure out how to build that. Okay? Type inference is a nice advanced feature that lets us get there. Okay? And then one last thing about this, type-driven development. Whenever you have a really powerful type system, you can write programs with just the types, okay? The functions and the type signatures. At Osberg, where I work, whenever we write a new microservice, it's not uncommon for us just to write functions and types, the entire microservice, before we provide any implementation at all. And then once it compiles and we understand that the overall structure of the code looks good, then we'll fill in the itty-gritty details about how those functions are going to be accomplished. But because we're using a strict programming language, I know that if I have that input mapped to an output, that whenever it compiles, it's probably going to work. All right? So that's type-driven development. Okay, how are we doing so far? All right, that's just kind of the basics. Even general purpose programming languages are going to support that. Probably nothing really groundbreaking there, all right? So let's go down a layer deeper, okay, into richer features of a modern type system. Okay, now this one a lot of us are probably already familiar with, but functions as types. These are called higher order functions. And what a higher order function means is that I can pass a function into another function as an argument, or I can return a function from another function, okay, as the return type. So in this example, I'm assigning to a variable a function, all right? Used in this way, this is an anonymous function, but I'm saying y is going to be an integer, and that is going to yield another integer. It's going to yield y plus 100. So I can call x, passing in 50, and I'm going to get 150. So integer to integer, all right? In this example, I'm going to define a function where in the formatter position, it's going to take another function as its input. So I'm going to pass in a sequence of integers, and then I am going to pass in a formatter that's going to take an integer and return a string, and that whole function returns a string. So it's going to loop through that list of integers, and it's going to run it through that formatter to generate strings and then concatenate that all together. So you can see I'm going to define f as taking an integer, and then I'm going to call that format function, and I'm just going to pass f right into it. And then I'm going to get that result at the bottom. All right? So that's higher order functions. This is kind of the rage these days with programming languages, because a lot of programming languages that did not start with higher order functions are starting to adopt them now. So C# supports these, Java is beginning to support these. Most of the functional programming languages already support this. JavaScript supports this. You get the idea. This is an example using a technique called partial function application occurring. Now this is syntax that's a little bit more specific to Scala, but Haskell does this very well. In fact, this is the only way you pass multiple parameters in Haskell. But essentially what I'm doing is I'm going to have two parameter lists, and I can apply the parameter list at different points of execution. So I can start out and I can provide the prefix string to my greet function, which I'm doing there in the hello greet, kind of in the middle. And then later on, I can apply the second parameter list. Okay, that process is called currying. And then so there I have hello greet, and I'm going to call it once with Jordan. I'm going to call it again with Alex, and I get two different results at the bottom there. So it's just late applying parameters to a function. All right, switching gears. So the question is, yeah, what is the benefit of currying? There's different benefits. So if you're in a language like Haskell, for instance, that's just kind of the way that you do it, right? So all of your functions are going to take one parameter, and you essentially, every time you invoke it, you're going to get another function that expects the next parameter until you get the result. When you study category theory, that is actually very natural with how category theory handles mappings from categories. But more pragmatically, it is kind of a way of doing dependency injection for your functions, if you want to think about it that way. So let's take the example where you want to make a call to a database, and you want to pass in something that's going to, like a parameter that's going to query the database on a filter. You might want to pass in the connection string of that database before you do your call, because you want to do injection on your configuration. But you don't want to have to do that all the way down at the point that that's needed. So what you can do is you can pass in like that config type early on in your program, and that's going to give you a function that's going to talk to the database that already has that baked into it. So then later on in your code, you can call it with the filter value, and it's already got that other one in place, and so then it'll run. So it kind of helps you from having like these really long parameter lists. You can kind of build it up over time. That's one example. There's several others, but that's kind of like a immediate practical one. All right, so let's talk about conditionals. Have you guys ever seen this? You know, people online talking about how if statements are evil. Does anybody want to take a bat as to why if statements are considered not great? You got to cover all the cases. Yeah. So. Exactly. Zach first. A lot of times they don't return a value. So you're not going to guarantee the output from that conditional body. Dylan? Exactly. So for testing, you have a lot of different conditions you got to check for, and so that's just more things you have to test in your code. Every single branch you got to take. Any others? Yeah, that's pretty good. If conditions are completely loose, right? You know, you can say if some predicate, else if some other predicate, else if some other predicate, but those predicates don't have to be related to each other, right? You can have something that logically makes sense in the first predicate, and then the second check, you know, maybe it makes sense or maybe it doesn't. You know, there's no enforcement by the type system there. So it would be really nice if we had native support for controlling that from our type system. So there's something that we have called algebraic data types that is one solution to this. Now, my Haskell people are going to say, well, wait a minute, algebraic data types are more than that. That's true. So let's kind of break this down. An algebraic data type is a variant type that supports sum and product algebras, all right? And it's going to let us do pattern matching on that. So what I mean is there's two things an algebraic data type lets us represent. Sum, meaning I can have an A or a B, but not both. And then there's the product, which says I can have A and B together. All right, now that's the conceptual definition of an algebraic data type. So let's break that down a minute. Product algebras look like this. This is stuff we know. A tuple is an algebraic data type of a product algebra. In other words, I have two types that come together. So in that first case, I have an int and a boolean. They come together as a package deal. And then the range of tuples I can support is all of the possible values for an integer combined with all the possible values of a boolean, okay? Classes, it's the same thing. At the bottom, I'm packaging together two different data types with that class. And that class, the range of supported values is going to be whatever I can put in an integer and whatever permutation I can put into a string, which is a lot wider, all right? Here's the more interesting one though. Sum types. A or B, but not both. So if you have been in functional programming at all, or you've seen any of our other talks here, we talk about like the option type. And you'll remember that option type is like it's like a base class, and usually you have a sum or a none. We're talking about the same type, and I can use them interchangeably, but the specialized version means two different things. I got either this or this, but not both at the same time. That's also true with the either, or sometimes called a disjunction. I got a right or a left, but not both. Or like a try type. This is more specific to Scala. I have a success or a failure. All right. So that's what an ADT lets you do. But the really cool thing about ADTs is you can do pattern matching on them. So instead of writing a bunch of if-else statements, you can pattern match on all the combinations, and the type system will enforce if you've covered all the cases. And if you haven't covered all the cases, you'll get a compiler warning. All right, so you can see in this example, we have an error as the subtype, or I'm sorry, the supertype, and then you got argument, parser, and runtime error that all derive from that. Each of those takes slightly different shapes in their constructor. Down at the bottom, I have an argument error instance, and then I can do a pattern match. I can say, okay, if that thing is an argument error, then handle it that way. If it's a parse error, handle it this way. If it's a runtime error, handle it this way. And if I leave off any of the cases, I'm going to get a compiler warning. That's going to say, hey, you're forgetting something. You need to go fill that in because we don't know what's going to happen when we get that match, okay? Any questions there? Dylan? Yes, so if you're in Scala, the sealed keyword is essentially the thing that's going to define that all of these types are together and it can't be further modified outside of that scope. In other words, you're not going to have a code file that's going to add in other extensions to it that are going to make your match statements break. That's more of a Scalaism. Mm-hmm. If you're familiar with C++, that might resemble an enum type, but enums, those are really just fancy integers under the hood. The type system's not going to do a whole lot for you there. These are a lot more sophisticated because it's actually the shape of the type itself. All right, polymorphism. Anybody want to guess? How many types of polymorphism are there? I'm seeing like, not sure anybody wants to say it. All right. Yeah, okay. So there's three kind of main types of polymorphism we talk about. So most of us are probably familiar with what we call subtype polymorphism and parametric polymorphism. So what that allows you to do is you have like a classic example is when you're using object-oriented inheritance. You got a base type, so let's say we've got a shape type, and you got specialized versions of that shape, triangles, squares, circles, and then each of those can give you like an area, right? And so I don't care what specific type I have, I can call dot area, and I can get back whatever that specialized type returns me. That's polymorphism at a subtype level. Let's look at the other two a little bit. Okay, well, I kind of already spilled the beans on that one. But well, actually, let's define this. Why do we use polymorphism? Mm-hmm. So it's going to unify a lot of different, it's going to abstract over behaviors. Exactly. So I can have a bunch of specialized types, but they all be unified and treated as the same based on common behaviors between them. Mm-hmm. Okay, so let's look at parametric polymorphism. Well, that's a $50 word. Okay, this is very similar. If you use C# or Java, this should be very familiar to you. Okay, essentially, this is the ability to say, I'm going to have a class, an object type, that supports some other data type in it. So a very classical example is a list of T. I don't care what T is. I don't care if it's a list of integers. I don't care if it's a list of strings. I want to support just a generic list of things. And I'm not going to do anything with those things, but otherwise just manage the whole lot of them, right? So this syntax is probably similar if you're like in C# or Java. It's going to be angle brackets, but you get the idea. This is just straight up generics, okay? That's parametric polymorphism. So in this example, we're modeling vehicles, and at the top we have an interface or a trait called the thing. We have vehicle, car, Jeep, motorcycle, and randomly thrown in a vegetable. And so you can kind of see how those all derive from each other. And then we're going to have a class that represents parking that's going to take a type into it. We don't know what type, but it's going to take a type. Now, if I create a parking that expects a motorcycle type, then I have to pass in a motorcycle to that. If I try to pass in a car, it's not going to compile because that is an instance that is expecting the type motorcycle, right? But I can change my example, and I can say parking takes a car, and I can pass in a Jeep because a Jeep is a car according to the type hierarchy. I can use type inference, so I'm not even going to specify a type here. I'm going to pass in 2 Jeeps, and the compiler, the type system, is going to figure out I'm talking about a Jeep, all right? Now, what do you think is going to happen if I take this exact same function, I put 2 different types in there? Let's take a Jeep and a motorcycle. What's going to happen at that point? Okay, both, yes. So essentially, it's going to go to the nearest common type of vehicle, all right? So if I pass in car and motorcycle, the nearest common type between those is going to be the vehicle interface. Now, this is something you might not have seen before, which is bounds checking. There's 2 different types, upper and lower bounds. There is another theory, you just throw that out there to sound smart, but essentially order theory says a partial order is a binary relation over a set P. So an A is, in that little symbol there, a less than, equal to, typically. B, we say that A is related to B, but does not imply B is related to A. The only reason I bring this up is because the syntax that you see in most of the functional languages comes from this definition. All right, you'll see an arrow with usually a colon or equal. So in this example, look at what we've done to parking. We say parking can take an A as long as it is bounded by vehicle. So in other words, I can pass in a Jeep because a Jeep is a vehicle. I cannot pass in a vegetable because that's not in the lineage of a vehicle. All right, so I've put what's called an upper bound on that type. And you can get more sophisticated where you can have upper and lower bounds. So I can say an A where it's between a Jeep and a vehicle. Any questions here? All right. Existential types. This is whenever you need parameterized types, but you don't really care what it is. So the syntax you can use is an underscore. So in my list above, I have a list of T, but you'll notice in my implementation, I don't use T at all. It's irrelevant what that is. So I can just say underscore, and it just means whatever. That's not important. It's just a generic type. As long as it's using parametric polymorphism, move on. All right, so that's existential types. Not a whole lot to say there about those. All right, for this, I'm going to switch over to some code. How many of you before have worked with type variants? Oh, great. Okay, cool. So let's look at this code for a minute. I have a series of types here. I got a person, grandparent, parent, child, grandchild. All right, I tried to keep that natural from kind of a top-bottom lineage, right, to make it clear. So I'm going to put this here. Get my cheat sheet. Actually, I just realized I'm kind of coming close to time, so I'm going to cheat. And we're just going to show the solution here. So I really want to get to the next one. The idea of variance is that we want to control what types in a range of types are available for subclassing. So when I say two types are variant to each other, that means the two types are equal. So a list of string is compatible with another list of string. If I have a list of string compared to a list of integer, those are called invariant. They're two different types, technically. But it would be really nice if I can define a function or a class that takes a list of a type and any of its derivatives. So I might say I want to create a type that would take a list of people, and anything else that is considered a person, I should be able to accept that too. That is called covariance. So that means that I am saying all these subtypes will be treated as instances of all of the higher types as well. So we can see that here. So in this case, I have denoted that this is covariant, and that's done in Scala by using a little plus. I start out with a function that I say, okay, it's going to take a box of a person, and then I can pass in any instance that is a subtype of person, and it will compile. So person, child, grandchild, grandparents. All right? Now look, in this example, I'm going to go one more. I'm going to define another function, though, that says it's going to be at the parent level. So I can pass in a child and a grandchild, but when I try to pass in grandparent, that doesn't work because that is in a different spot in the type hierarchy. Covariance is usually pretty straightforward to understand. It's when we talk about contravariance, things get a little bit more muggy. So real quickly, actually let me split my screen so we can see our types at the same time. Okay, look at this guy down here. When I say contravariant, all I'm really saying is it's going the other direction. I'm going to say I'm going to accept a type that is higher up the hierarchy but not lower. That's really what I'm saying when I say contravariant. It's the other way around. So I might take something that's a parent, I can take a grandparent, I can take a person, but I can't take a grandchild. Okay? Does anybody want to say why contravariance is important? Anybody want to take a swing at that one? Oh man, Dylan, go for it. Yeah, okay, so I'm going to apologize for this slide right now. This is a terrible slide, but I'm going to try, all right? This is one of the de facto reasons why you need contravariant when you're designing a functional programming language, or I'm sorry, not functional, just a programming language, this is in Scala, that's the definition of a function of one parameter. So in the standard library, that's what it looks like. You have P in a contravariant position, and R, which is the result, in a covariant position. And so this is the definition of a functor, an A to a B. And what we're saying is that we can take in a P and any type that is up the type hierarchy, so anything that's less specialized, we can accept as an input. As an output, we can return anything that is more specialized. What we're really saying is that if we're going to subclass that function, the inputs can only have fewer requirements. You can't pass something in that's going to have more requirements, but the outputs must at least be as specialized because the caller expects those to be available. All right? So in other words, I'm not going to return something from a function that has fewer things than what I expected out. Anyway, I'm not going to go into that. If you're interested in learning more about contravariance, I'm going to share these slides afterwards, and there's a link at the bottom that goes into some really nice details about that. Okay, this is what I really wanted to get to, and I've put myself on a wall because I only give myself about 15 minutes to do it, but type classes. These to me are really exciting, all right? How many of you have used type classes before? Scott? Yeah. Okay, if you're in Haskell, that's all you got. If you're in Scala, it's kind of weird. Okay, type classes are well, actually, let's just dive in. What are the disadvantages of object-oriented inheritance? Help me out here. What are some problems with inheritance? It's unclear how the inheritance tree should look. Do you mean like, you know, like what abstraction you should take? Yes. Yeah. Designing abstractions through inheritance is really hard to get right. It's easy to start dropping inheritance in, and then somebody else comes the way and says, oh, I need something. Hey, it kind of looks like this super type. I'm just going to inherit from it. And then before long, you get like this just mess of inheritance, and everything's at the wrong abstraction. Oh man, yeah, multiple inheritance, where you get like all kinds of diamond-shaped patterns or circular things can really make it hard. Like if you have like a diamond pattern in your inheritance and both of them define the same base like member, like which one does it come out of? Which one does it call? Yeah. Any others? Violates encapsulation because now you've got multiple classes that are going to borrow the same members. In a sense, you've tightly coupled those. So modifying them can become harder, especially when you start using that all through your code base, and then you got to modify your your inheritance hierarchy. You get into problems real fast. I hate reading code that uses inheritance. Oh, I hate it, hate it, hate it. It's great if you're reading, like writing it, but then once you need to like, you're in somewhere, it's like, where did this member come from? And you're looking through files, and you know, if you're using an IDE, that's one thing, it can kind of help. I like using Vim. Don't get a lot of help, so now I'm looking through files and I'm frustrated, okay? Reuse abuse, we talked about that. We are really bad at following dry correctly, okay? And also, if you're using a library that gives you types, you can't do anything with that library, right? You can't add inheritance to something that you don't own in your code base. And that is where we're going to get into type classes being incredibly important. Okay, so commonly we hear of a composition as the solution to inheritance. Use composition instead of inheritance where possible. There's a couple other things. But what about another way, all right? What if we wanted to add behavior to types we don't own? That's pretty cool. What if we want to selectively apply behavior in different scopes of our code base? Yeah, people are getting excited right now. I know, I can't hear Tulsa, but I know they are flipping out right now. Okay, what if we wanted to apply lawful behaviors to our abstractions? Yeah. Man, I'm excited. I'm just really excited. Is he? Oh, this just got even better. All right. He probably is there. He's on Meetup. He saw this. I know he's sitting there. Darren high-fiving him right now. Yeah, type classes. These guys are pretty cool. The idea with a type class is we're going to separate behavior from data. So when you're coming from a classical object-oriented background, you're going to put the two together a lot of times. You'll have objects, and those objects are going to have methods, right? So the methods go with the objects. There's a totally different paradigm, though, where we're going to separate out behavior from objects completely. So we're going to have the data type, the structure. We're not going to apply any methods to that. That's going to be defined separately, all right? Now, some might say, well, I can do that with interfaces or traits, but you can't really do anything, though, about those data types you don't own, all right? That's still a problem. So here's what a type class does. Oh, wait a minute. Okay. There's a slide I meant to have in there. Type classes kind of turn the idea on its head of the ownership of functions, all right? With type classes, we're going to be behaviors first, and then the data comes second. Whereas in object-oriented programming, it's the other way around. The objects come first, the behaviors come with, okay? So here are the elements of a type class. Now in Scala, this is a little bit awkward. Haskell, this is just how you do it, right? You use type classes all the time in Haskell. But you have the behavior that you want. So this commonly comes down to a trait or an interface. You have instances that for each of the data types that you want to apply that behavior to. So if I'm going to be working with people, I want to apply behavior to a person type, I'm going to have a concrete type for that. Integers, strings, those are going to have their specialized implementations. And then I need some sort of interface that I expose to my users through my API. So here's what this looks like. The behavior's at the top, and then you're going to have your function that requires that type with a behavior. So I'm going to write a function that says you can pass in anything to me as long as it has the behavior that I expect. All right? And so then it's up to you to just provide those behaviors for whatever type. So how is this different than interfaces? All right? First of all, I get a compiler error if I try to pass in a type into my function that does not have that behavior come with it. I can import those behaviors into different scopes. So I can say, in this part of my code, I'm going to bring in these behaviors from this, this list of behaviors over here just for this area. It doesn't have to be holistic through the code base. I can also provide behaviors for types I don't own. So if I'm using a really sweet, type that like library I get from somebody, I can create behaviors on how it would interact in my own code base, and then suddenly I can now use that type with other behavior libraries out there. And it's really easy to drop in new things. Okay, and I already said this. Essentially, we're flipping, instead of thinking about classes carrying behaviors, we have templates of behaviors, and then we're bringing along interpretations for different types. So here's an example in Scala. This is awkward in Scala. Unfortunately, this is not a first-class citizen in Scala. It's an idiomatic pattern. If you're in Haskell, this is built into the language. But you can kind of get the idea, though. We have a sealed trait at the top. Okay, we're going to represent a JSON type. All right? And then we have different JSON things. We're going to have a JSON object, a JSON string, a JSON number, and then JSON null. All of these extend from JSON. All right, so that's just defining my types. Now, the JSON writer, that's the behavior that I want to create. I want to be able to take in a thing, okay, type A, and produce a JSON from it. Anything, I want to produce a JSON, all right? That's the behavior I want, A to JSON. So the next step I got to do is I have to define the implementation of that behavior for the types I care about. So I'm going to do it for two different types. I'm going to do this for strings, and I'm going to do this for a person type. So the string type essentially says, okay, we're going to override the write method. We're going to convert that to a JS string and return that out. So it takes a string as the input, and then it's going to return a JSON string out. For the person type, which I've defined above, it's going to take in a person, and then this is going to create a JS object with the attributes broken out, the key value pairs. Now this is where it gets great, because now I can define a function that says to JSON, and what I'm doing there is I'm saying with that implicit, I'm saying whatever A is, there has to be a JSON writer for type A in scope. So in other words, that behavior has to be present in scope to work. And so down at the bottom is what I finally get. I'm going to say JSON.toJSON. I can pass in a person, and now I'm going to get out a JSON object. I can pass in a string, and now I'm going to get a JSON object out of it. Where you really see this is libraries like, if you're in the Scala ecosystem, you see this with Scala Z or the CATS library. Those are just type class libraries. And what they are is they're behaviors for category theory. And so you get all the semi-Drupal, the functor, the folding and catamorphic capabilities. You get monoids and monads. You have all those lawful behaviors defined in Scala Z and CATS. And then you get a whole bunch of implementations of those behaviors. So you just drop it into your project, and suddenly all of your types can now work with lawful behavior. Okay, so pretty cool. I'm going to skip this. Yeah, Haskell does it really well. Scala could use some work. We're not going to get to higher kind of types, and that's it.